Look at the handout that I gave you guys. Go on Blackboard. Yeah, very good. It's small representation of the entire thing. So everybody open up the, go to this week's folder and open up, it says Introduction to Hypothesis Testing, and then Introduction to Hypothesis Testing again. I want to look at this problem here. It says two-tailed hypothesis, suppose the math department ordered blah, 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 blah. Okay, can I get somebody to read that for me, just to make sure you guys are awake? Can somebody turn on their mic and it says, suppose the math department orders. I don't care who does.
I'm gonna read. So,
yeah.
Suppose the math department orders colored chalk from a company. Ultimately, the math department will place the chalk in a chalk holder. It's important that the incoming shipments of chalk maintain an average thickness of 0.56 millimeters, because if it falls too much outside of this range, it will not fit into the holder. If the department notices that the chalk is not fitting, it will send all chalk back and request a refund. Of course, the company that sells the chalk claims the average thickness is in fact 0.56 millimeters. Let's say we take a random sample of 36 pieces of chalk and find the X bar to be 0.553 millimeters and is that standard deviation? The S to be 0.03 millimeters. What do we conclude about the company's claim that the chalk maintains an average thickness of 0.56 millimeters?
Very good, thank you, very good. So, okay, so you can kind of see the setup of the problem, how at the end of the day, we have to make a decision. Do we send the chalk back or do we keep it? The company made a claim. So what our job is to do is to put their claim through a statistical test to see what the result is going to be. All right. So thank you. I forgot who that, I didn't know who that was who read. Who was that read?
That was me, Talia.
Talia. Okay. Thank you. I appreciate that.
No problem.
Okay. So let's now get into the crux of this thing. And I'm going to draw this diagram and I'm going to try to explain what's going on here. Now, we took a sample. So we got all this chalk that's been delivered, boxes and boxes and boxes of chalk. And we took a sample of 36 pieces. So that's like how large our sample is. Okay, we're going to come back to that notation in a minute. But I want you to see what's going on here. Let's say, for example, we take this chalk and we just open up all the boxes and we just look at one piece of chalk. And we record, I guess, whatever the, how big it is in terms of the dimension. I forget, I know it's in millimeters or whatever. So let's say the first one that we get, let's say X1, let's say it ends up having measurement of 0.56. So I'm going to write this right here, 0.56. I'm going to say X1. So that's the first one. X2. Now you're saying, where are these values coming from? I'm just making them up just to kind of prove a point. And let's say 0.57. Oh, that's right here. So that's X2. Now I can go through, let's imagine if there are like 1 million pieces of chalk in the shipment. By the time, oh, okay, so actually you can see. So by the time I get finished observing all the chalk, one by one by one by one, it may be this one's down here, maybe another one right here, maybe another one right here, right? And let's say I look at each individual chalk piece and I draw a diagram, let's say X6, let's say X7, and let's keep going all the way to like X1000 or X1,000,000. By the time I get finished plotting these, this may stop right here, this may stop right here, this may stop right here. And so once I sort of draw the diagram, it may look something like this in terms of the heights of all the dimensions. It may look something like that. Real ugly, just real ugly. In other words, this point right here represents how many of them were like 0.55. This would be how many like 0.7, right? And let's say it goes all the way up here. So this right here is called a distribution, right? Real ugly, just real ugly. It doesn't matter what it looks like. But this is a distribution that comes from taking one at a time, you know, and putting the values in terms of where they are. See, this can keep going all the way to like x 1,000, let's say 0.52, that's over here. So at the end of the day, I'll have this many that's this high, this many that's this high. And if I just sort of connect the points, this becomes what it looks like in terms of what I'm going to call the population distribution. Population distribution, because that diagram came for taking one observation at a time and graphing it. Just one at a time, no sample yet. I'm literally opening up every single piece of chalk that's shipped. Let's say 1 million pieces. So then I have 1 million places on here. But now what happens if I do this? As we just heard, what I'm going to do now, I'm not going to just look at one at a time. I'm going to take 36 pieces of chalk. 1, 2, 3, 4. So at the end of the day, I'm holding 36 pieces of chalk. See, that's my sample. And what I'm going to do is now look at these 36 pieces of chalk, and I'm going to find the average of these 36 pieces. And here's what I'm going to do. I'm going to say, let's write this so you can see it. The sample, I'm going to say X bar. I'm going to do this a different color. If you have a different color, X bar 1. Let's say I take those 36 pieces of chalk and I get an average of 0.56. So I've gone now from observing one chalk at a time to gathering 36 of them, a sample, and finding the average of those 36, and I'm writing what that average is. So here on the same chart, I'm going to have X bar 1 being right here, this 0.56. So this green value right here represents taking a sample and putting it on this same chart. Now, let's throw those 36 over to the side. Let's do it again. 1, 2, 3, 4. Now I have another 36. Let's take the average of those. This time it may be X bar 2. This time it may be 0.55. So now I'm going to go here and say, here's X bar 2. So notice the green comes from me taking a sample, taking the average, whereas the black is 1. Everybody follow me? Is that okay? Now I'm going to skip ahead, and I'm going to do this only because I know that it's going to be true. This population graph looks like this. It could look like this. But in statistics, when we start looking at samples, as long as the samples are large enough, and in general we say at least 30 or more, this graph down here is going to have a certain shape. It's going to look like this. Can you all see that? Can you see that? It looks a special way. In fact, we're going to call this green the sampling distribution. The sampling distribution, because it arises out of taking samples. Okay, so understand conceptually the difference between the black graph and the green graph. The black graph comes from looking at one piece of chalk at a time and graphing the results. This green graph comes from taking a number of them in the sample and finding the average of those, and I'm plotting the averages. And so what this does is give us, and so this whole thing here is something called the central limit theorem, where as long as my size of the sample is large enough, this sampling distribution is always going to come out to look like this, which is called normal, a normal curve, like a bell curve, right? So this green here is like looking inside of here, the sample, the cup, whereas this black here is like looking inside of the entire pot of soup. So just like we're only going to focus on this cup to make a decision about the pot, I'm only going to focus on this green to answer the question that's posed to me in this problem. Everybody see that? Okay. So how are we going to solve the question that we just were addressed? So just for clarity, allow me to, I'm going to erase this and I'm going to blow up the green graph. I'm going to blow up the green graph. So I want you to see if you can follow me here. Because when you have problems like this, even in your homework, you're only going to be dealing with the green graph. Okay? So I'm going to do this. I'm going to blow up this green graph. And then I'm going to do this right here. So this black right here, what I just did, is assuming that it's like the population, that real ugly curve there. And what I'm focusing on right now is I just blew up this green graph, right? So again, this green graph is like focusing on the cup, right? Any questions so far? Any questions? All right. Well, again, this is the sampling distribution. Sampling distribution. And there are two things we got to note about the sampling distribution. And, you know, I still have this question here that we have to think about with the chalk. Still have this question. But let's set up the sampling distribution. As long as the sample is large enough, and I'm going to go ahead and write this here. I'm going to say n equals. This n right here, and we did not define it earlier, but this n here is going to be the size of the sample, right? In the earlier example of homes, I think it was 30. In this particular problem, I'm kind of jumping ahead, but can anybody tell me what you think n is in this problem that we just read? N is the size of the sample that we're going to focus on. How large was the sample?
36.
Is it 36? It'll say like random sample or something like that, or n. So even if it doesn't say n, if it says random sample, then that's how large, that's how many pieces of chalk we use to do this test. All right. Okay. And again, I apologize, I'm going really, really slow and methodical, but I think this is important to make sure you kind of understand kind of where we're going. Okay. Notice here, when we use this thing called the central limit theorem, we have this sampling distribution. It's normal. So I'm going to write an n right here. The shape of it is bell-shaped. It's always going to come out to be that when we do hypothesis testing. It's normal, and it has two things that we have to look at: the mean of the distribution and the standard deviation of the distribution itself. So if you look here, the mean of this thing is always going to end up the mean of the population, right? You can't really see this black part anymore, but we're going to assume that the middle here is going to line up with the middle of this black distribution that I erased. So I'm going to say this is mu sub x bar. In other words, I know it looks crazy, but this sampling distribution is going to be normal. That's what the n stands for. And it's going to have a mean that's right in the center. It's going to be the same mean as like the black distribution, but I'm going to call it the mean of the smaller distribution, mu sub x bar. This is the x bar distribution. So it's going to have a mean that's going to be the same as the black. And then I'm going to write this: sigma X bar. So I don't want you to get confused over the notation. All that means is this green distribution is going to have a certain mean, which is going to be right in the middle. It's going to be equal to the mean that's given. And it's going to have a certain spread for the X bar distribution. And we're going to talk a little bit more about what that means in terms of solving the problem. Because you're going to need to know those two values there to help get you out of this particular situation. Okay, so just write that. Now, let's see what this means in terms of how to solve this particular problem. Now, and then what we're going to do is go step by step. We're going to go step by step to figure out how to solve the actual problem itself. Now, this mean here, we're going to find out is 0.56. And often, we're going to put right here in terms of what is claimed in the actual problem. Okay. Now, if you sort of read the problem here, the people who sent the chalk claimed that the width of the chalk was 0.56. So generally, whatever's being claimed is going to go right here in the middle of the distribution as your mu, right? That's going to be kind of what's claimed. And here's the whole point with hypothesis testing. You're going to sort of almost do it like if you go to court or if you're doing like a law, if you're doing like trying to prove something, or if you're like in a debate class. The debate class says, well, let's assume that's true. And then from there, they kind of shred your argument to shreds, right? So the whole point of hypothesis testing is you have a sampling distribution, like your cup, and you're assuming that what the claim is true, and you're going to see if it's true where your value that you found in your problem lies on a certain trend. Okay, so just in general, we have this value here, which is like our mu, 0.56. And eventually what's going to happen is, I'm going to draw this here. I'm going to draw this here. Okay. So here's the notion. Here's the notion. The company claims the average thickness is 0.56. They claim that it's this. We found the average thickness in our sample to be, I think it was 0.553. Yeah, we found it to be 0.553. Is 0.553 close enough to 0.56 that we'll say, it's okay. It's not that far away from 0.56. Let's just keep it. Now, clearly, if we found this to be 0.56, we don't even need to do the test. Because, see, what we found matches this identically. But how much wiggle room do we have if they claim it to be 0.56, and we found ours to be 0.553, how close, is it close enough to this 0.56 to say we'll still accept the chalk as being from a population of 0.56? And you see these values I put right here? These are what's called cutoff values to accept or reject the claim. So inside of here, I'm going to say accept. In other words, from this 0.56 up to some value right here, and to some value right here on both sides, I'll say it's still close enough to 0.56 that we'll go ahead and accept it. Versus if it goes beyond this value, or I don't know what it is, let's say if it's 0.57, I don't know. And let's say on this end, let's say it's 0.54 or something out on there. See, in other words, whatever these question mark values are, say keep the chalk, 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 boom, send the chalk back. See that? On this side, 0.561, 0.562, 0.563, keep the chalk, keep the chalk, keep the chalk. But as soon as it goes beyond this value right here, I'm going to send the chalk back. So I'm going to call this rejection region. Reject, reject. So the whole point of the test really is to figure out at what point in the threshold do I magically go from accept to reject, send it back. And then on this side, at what point do I go from accept to reject? If this 0.53 in a sense ends up over here or over here, then that's going to determine whether I'm going to send the chalk back or not. Okay? That's the general idea. So the hypothesis testing, and when you have two of these rejection regions right here, that's what's going to be called a two-sided test, two-sided hypothesis test. In this class, we're only going to deal with two-sided. We're not going to deal with one-sided. That's for your 222 class. In fact, the good part of this review is that we're only going to look at situations here where n is large enough, this random sample. So we're going to always assume generally 30 or more. Okay? So we're going to write the 3 steps of a hypothesis test. We're going to come back to these in just a second because we're going to need these in order to solve the problem. But does everybody kind of understand the basic setup or the basic mission of the test? I'm only going to look at situations where I'm looking at the green. In other words, in the problem, they always have to tell me what our X bar is that we found when we did it. And I know this chart right here comes from doing X bar 1, then doing it again. Look at another sample, then another sample. That's where this distribution comes from. But in real life, we make a decision just based on one X bar, right? In other words, I don't dip the cup in the jar, make a decision, throw it out, dip it again. That's the second time. Dip it again. I don't have to do it 36 times. What the thing is, I dip the cup inside of here, and I only do it one time, and I make a decision just based on just doing it that one time. I don't have to do it 36 times. I'm sorry, it's not just, I don't have to do it 36 times. I'm just going to do it just that one time, get that one average, and then that's it. So let's write down some steps. And this is now officially solving the problem. All right, so let's say step 1. And this is a strategy in your notes when you do your homework. These are the steps that you're going to use to do your homework. And it's also the steps you will do on the exam. So let's say, okay, and so essentially when you do hypothesis testing, you're pretty much testing H sub 0 versus H sub 1. So I'm going to say step 1. Now we're officially solving the problem. Establish a safe area by setting up your initial conditions. There are 3 initial conditions that we need. H sub 0, H sub 1, and something called alpha. Right, so this is step 1. Establish a safe area and really non-safe area by setting up your initial conditions. So in this problem, we need to write all of these down. H sub 0, H sub 1, and then say what alpha is. Now I'll tell you what alpha is in terms of the diagram in just a second. Now, remember what the definition of H sub 0 is? H sub 0 is your null hypothesis, the claim. What is being claimed in this problem? that the average thickness is 0.56. Okay, so whatever the claim is, that's what I'm going to have to write for mu h sub 0, and it's going to be this: mu equals 0.56 in this problem right here. See, they're saying the average thickness of all of the chalk is 0.56. You're saying, wait a minute, I thought you said we're going to be using the cup. We are. But when you write the h sub 0 statement and the h sub 1 statement, you have to write it according to the population, or like the big pot. Okay? What's your definition that we wrote for h sub 1? What do we have to write here in terms of h sub 1? It's a competition, like a boxing match. Based on what we wrote for the definition of h sub 1, what is h sub 1 in terms of an equation? Look back at your notes and see. Yeah.
The opposite of h sub 0.
Okay, good. And so in this case, it's going to be what? If h sub 0 is mu is equal to 0.56.
Is it negative 0.56?
Not quite. But I understand where that's coming from. If I say, well, the opposite of equal. Good, not equal. Yeah, so here we go. Right. Yeah, so we won't necessarily change the sign of that. So the competition here is either the average thickness is 0.56 or the average thickness is not 0.56, right? So it's going to be the opposite of our null hypothesis there. Very good. Now this alpha is just what they call a level of significance, and generally it's always given in the problem. I did not give it in this problem here. So whenever it's not given, we always resort to 5%, which is 0.05. But generally, the problem will have to tell you what alpha is, 0.05. And this represents that rejection region. Remember the diagram that we had? So it looks something like this. So here's the 0.56 right here. And then I said here, and then here, and then these two parts right here were the rejection region. Okay, so that's what I'm calling alpha, the area in black on both sides, right? So it's 0.05, and again, it's nothing magical with this number. It's just normally what people use when they solve statistics problems. But in your homework, I think they changed this value some, like 0.01, 0.05. Well, what's the point? Why is that important? If this part here is 5%, what must this part be right here? Assuming that the total area under there is 100%. What must this part here be if this is 5%?
95%.
95%, very good. See, so all of this inside of here that's left over. So in other words, this 95% plus this 5% represents all of the data underneath the curve, which is 100%. Okay, but be careful here. See, it's not 5 here and 5 here. These two together are 5. So it's like 2.5, 2.5 right here. Okay, and so I'm saying 0.05. But so that's what it is as a decimal, but as a percent, it's 5%. Okay, so we set up our initial conditions. Always, you just have 3 things here that you have to state, and this is based on the reading of the problem. So this always represents what is being claimed, and a lot of times they actually use the word claim. And I have to use mu equals that, the opposite of this right here, throw that negative sign in there, and then write down what alpha is. Step 2. Step 2. Step 2. Assume H sub 0 is true. That's just standard with hypothesis testing. Assume H sub 0 is true. Use alpha to find the cutoffs. Okay, let's draw this again. Here's my 0.56, that's my claim. Assume that this is true. You remember that it's two cutoffs, one right here and one right here, in terms of question mark. So assume H naught is true. I need to find this cutoff value and this cutoff value right here using alpha to find the cutoffs. Okay, so we kind of did that. And you kind of told me before, if alpha is 5%, that means this inside of here is 95%. Now here's a trick question. What percentage must be right here? And what percentage must be right here? Think carefully. If this is 5%, that part there, and this is 95% here, what do you think this chunk is? And what do you think this chunk is?
47.5%.
Yeah. And the reason that's true is because of the idea of symmetry. Have you guys heard of symmetry? Right? It's almost sort of like the mirror image. Right. So that's good, Lily. Yeah. So 47.5% here, just divided by 2, or 0.475. Same thing here, 47.5%, or 0.475. So I wrote it as a percent here and as a decimal right here, just by moving the decimal twice. But notice here, notice that the percentage right here, so this 47.5% is going to be this part right here. Notice that this percent here is based on what alpha is in the problem. If I change alpha to like 0.02, then clearly this number is going to change and that number is going to change. Okay? All right. Is everybody with me so far? Is everybody with me? All right. This information right here is going to help me determine what that cutoff is and what that cutoff is, using something called a z-table. Right? Now, this whole notion of z, and I guess I better define it. But in the meantime, go to Blackboard and open up that z-table. There should be a z-table I put on Blackboard. If you have the book, it's the last page. If you have the print version, it's like literally the last page of the book. But as a courtesy, I uploaded it for you. All we're saying with z, okay, let's see if I can try to explain this. Let's say definition. A z-score represents how many, a z-score represents how many standard deviations you are. A z-score represents how many standard deviations you are away from the mean. Away from the mean. And what happens is we have to use this notion of z-score to help us figure out a problem like this. Because let's say in another problem, let's say you're dealing with heights, and you say the height is 6 feet. Well, in this problem, we're dealing with measurements of chalk. In another problem, we deal with salaries. But there's one scale that we can use that brings everything to the same scale irrespective of whether we're talking about height or salary or thickness of chalk, it brings everything back to that same scale. So that's what that Z thing does. So if I look at this mean right here, 0.56, how far is 0.56 away from the mean of 0.56? Nowhere, right? In other words, the Z-score of the mean will always be 0. Because by definition, the Z-score is how far is that value from the mean? Well, if the mean is 0.56, how far is 0.56 from itself? No. So that's why we always say Z equals 0 here. But now the challenge is to find out what is the value of these question marks here as a Z value. Okay? So the mean is always going to have a Z-score of 0. But these question marks, we need to know Z equals question mark, Z equals question mark right here. Because once I find the values of this Z here and this Z here, I now have the cutoff of the problem. Now go to your chart. Go to your chart. Notice how at the chart up here, it's giving you values based on, look at the diagram, from the mean, which is 0, out to any stopping point, Z. Now you see that shaded value there in purple or whatever, you know, it has like an A there. That's like this part right here. That's this part right here. That's this. Which looks like it's 0.475, right? So go inside of the chart and see if you can find 0.475 somewhere. Oh, I see it. I see it. I don't know if you can. So what you're doing, you're going inside of, because these values in here represents like the percentages or the decimals, which is this thing right here, 0.475. And I don't know if you found it yet, but it looks like this. Wait. 0.475. And it goes over to some number over here, and it goes up to some number up here. Everybody see that 0.475? If you go to the left, what Z does that stop at? I don't know if you guys can see it. If you look at the chart and you find 0.475 here, I need to go over this way a certain amount and then up that way a certain amount, because that's going to help us find the Z-score. Yeah, very good, Kiara. 1.9. You guys see that? 1.9. And then how far does it go up? How far does it go up? What is that? Yeah, 0.06. Do you guys see that? You guys see that? Right? So what I did was find the decimal inside of here and then see how far does it stretch that way, then how far does it stretch up. Oh, so then that suggests that the Z-score associated with 0.75 is what? Put it all together. Good, good, good. Very good. See, 1.96. See, I go over here, the 1.9, plus value up here, 0.06, put it all together, and I got that 1.96. Excellent, very good. You guys are following me. See, that's good. That's good. All right. So right here, I'm going to say Z equals 1.96. Okay, the problem is coming together now. Because see, that's the challenge. Figure out what the cutoff is that goes from the acceptance region to rejection. And what is this one over here? It's 1.96. What is this one over here on the left side? Because see, I don't see any negative values on the chart. That's 1.96. Well, because of symmetry, this is going to be a negative 1.96. Okay, so the chart does not give you those negative values here, but you can see that 0.475, and any values to the left of this z equals 0 are going to be negative z's. To the right of that z equals 0 is going to be positive z's. But as long as this 0.475 is the same as this 0.475, because of the symmetry, there's the positive version there and the negative version over there. All right? I think you guys are following me. I think you guys are following me. Now, if this was something like 0.28 and this was like I don't know, 0.37, then I just can't use the same numbers right here. This is only allowable only if this number right here is the same as this number right here in terms of the percentage. So step 2 is done because I found the cutoffs. Here's the first cutoff, z equals 1.96, and here's the second cutoff, z equals negative 1.96. But notice how we did it. We had to have alpha first, 5%, 5%, because then that let us know what this value was, 0.475. As soon as I know what that number is there, I've got to go to the chart, look it up inside of here, and figure out what z-score you have. It's not always going to be that simple, because suppose you have a number, let's say you have, let me make something up, 0.8. Suppose you have something like that. Suppose you end up with, inside of here, you have something like 0.0478. Now, in our situation, the number was there. But if the number is not there, just use whichever one is closest to, right? So there's a point, oh, I'm sorry, not 0.04, 0.4.
We can't see you.
Oh, really?
Okay, went out.
Okay, let me see. Did it come back on?
No.
So what are you able to see? Like what can you see now?
Just says your name, and it says like the video is out. Now it's
Okay.
back.
Okay, 1 second. You may be doing this. I may
back.
need to. Oh, is it back on?
Yeah.
Okay.
I
Let
think
me.
the connection went out.
Okay. All right. Because my juice is sort of getting low as well. Give me a second. Let me plug this up. Okay. And normally I won't talk so much, but this first day I just have to make sure. Okay. Is it back on?
Yeah.
Okay. All right, so what I was saying before is you may not always end up with a number that's like pretty or that's in the chart. Like in the case I made, I don't know, if you have 0.4757, then just use whatever number's closest to it. Like in this case, it'd be like 0.756 or something like that. So whatever is closest to, just use that, and then just use that particular z-score. Okay, last step. So I'm going to leave that there. Is everybody okay about where these cutoffs come from? You have to be comfortable using this number and using the z-table to find off those particular cutoffs. All right, final step. And we can go get some lunch. Step 3. Where are we? Accept or reject. Accept or reject h sub 0 using the x bar you found in your test. accept or reject X bar using the X bar you found in your test. So this is pivotal. I'm going to draw this again without all the distractions. I'm just going to put the actual values on there. So here we go. We have this, z equals 0. We found this to be negative 1.96, and then this to be 1.96. Okay, so I'm assuming you guys know where that comes from now. Remember, this is the acceptance region. This is reject. This is reject. We need the punchline. Step 3, accept or reject X of 0 using the X bar you found in your test. In our problem that we just read, what is the X bar that we found in our test? We took our chalk and we found sample to be what? I think it's 0.553. And that's a challenge with these problems. Like, you have to be able to sort of read a paragraph and figure it out. So the claim is 0.56. But we took the 36 pieces of chalk, found our average, and it ended up being this, 0.553. We have to figure out, where does 0.553 fit on here? What is going to be, does it fit in the acceptance region or the rejection region? And I hear you. You're saying, what are you talking about? Because see, these are Z's right here. These are X bar, but we transformed it to a Z. See, these are Z's, and what we found is in terms of X bar, 0.553. So there's one final step we have to do. We just have to simply change this X bar that we found to a Z, and then we'll be able to see where it fits on side of here. Okay? And we have to use this formula. Z equals X bar minus mu over S over square root of N. Long story, but that's what it is. Okay? So, again, so far, we have the different pieces up to step 2. We found that 1.96 is negative 1.96. This Z for the mean is always 0. I need to figure out, where does this value, X bar, fit inside of here? And so you're asking me to compare apples with oranges. Well, just turn this apple to an orange, and then you'll be able to figure out where it fits. Okay, so here goes. Let's do it. Ooh. Whoa. Let's do it. Z equals, what is the value that I'm trying to turn into a Z? It's the value that I found in my test, 0.553. See? That's what I'm, this 0.553, if you get like the student read earlier today, this is what I found when I did my test, when I got all 36 of those pieces of chalk. And so that's the boxing match, comparing this 0.553 to, what's going on inside of here. All right, minus, what is mu? We're assuming mu, 0.56, because we're assuming it to be true, divided by our standard deviation, or S, 0.03, divided by the square root of N, which in this case is what? How large is our sample? I think 36. Yeah. So if everybody find that for me. I apologize we didn't have another break, but this is the only time we'll really do this. I want to see what you guys know about algebra. I want to see what you get when you find this answer right here. I hope you guys have a good calculator too. I have a TI series. Anybody want to take a stab at it? Tell me what you got.
Is it negative 1.4?
I think so. I think so. Anybody get something similar? Okay, good. All right. So now do you see how we can now superimpose this part of the problem into here now? Because everything is in terms of z's, right? I could have changed these right to x bars, but that's double the work, right? So negative 1.4. So according to what you see here, does it fit inside of the acceptance range or the rejection region? Right? Because here's the 0. Then positive, positive, negative, negative, negative. Do you think it's in? Yeah, you see that? See how this negative 1.4? See how it's between this 0 and the negative 1.96? So it's, oh, I don't know, maybe somewhere here. See, once you get past here, that's getting into like negative 2, negative 3, right? So I want to say here, z equals negative 1.4. Because that's where my x bar fits for the value that I actually did. See, negative 1.4 is inside of here. If it goes beyond this negative 1.6, like negative 2, negative 3, or positive 2, negative 3, so all of this inside of here says, and we're going to write this last statement here. See, as long as the value falls inside of these two values there, we accept the x of 0. So let's write the final statement. We did all that to, just to be able to write the final statement. Is everybody understanding where this negative 1.4 comes into play? I'm taking the value that I found when I did my test, changing it to a z, and then seeing it was found there. A lot of times I call this ZT for test, and these z's right here, ZC's for cutoff. Okay, let's write the final statement, and then we're good to go. And here's the final shebang. Solution. Since our test statistic, and I'm going to write what it is, z equals negative 1.4. That was what we just did. Is in the acceptance region. Since our test statistic is in the acceptance region, then I'm going to write what the acceptance region is. Negative 1.96 to 1.96. See, that's the acceptance region. This cutoff and that cutoff. Is in the acceptance region. We accept x at 0, right? So the only thing I did was just rewrite what x at 0 said earlier, like in the boxing match. See, this is real weird. This is real weird because we did all that work on the cup. We did all that work on this, and now we're making a final statement about the pot. See that? So whenever we make this final statement, we always have to go back to mu, which is like the larger population. And let's say this means that the average we got, this means that the average we got from our sample of chalk, I know this was a lot, but I'd rather do it this way, falls inside of the range. Okay, this means that the average we got from our sample of chalk falls inside of the range where we would expect them to fall, if H sub 0 is true. This means that the average we got from our sample of chalk falls inside of the range where we would expect them to fall if H naught is true. So we blank. What you think? All of that just to say what? Because what did the problem ask us? What's the final thing we need to put there? Dana, yes. Yes. See that? Because see, remember the whole point, and I know it's got it kind of cloudy, but the whole point was, are we going to keep this chalk or send it back? Right? So we had to use all this mathematics to make a decision. See? So we will keep the chalk. And actually, what the other student said, that's exactly correct as well. But notice how when we're doing this problem, we do all this boring math, all this boring math. But then at the end of the day, we need to be able to turn it into a decision and tell Joe Blow, who hasn't taken anybody's stat class before, okay, according to my calculations, keep the chalk, don't send it back. Right? So this is kind of involved, and I really kind of went over like 3 classes at once, right? If I were teaching this in the 222 class, we probably spend like a week or maybe a week and a half on this right here. But because of what we have to go in this course, I kind of had to squeeze it into like a little pint-sized kind of presentation. But I mean, I think you guys really were following me. I mean, now you may have to sort of refresh, but I get the feel that this is not over your head, that it kind of rings the bell a little bit. I mean, I think you guys are okay with this. Now, you're going to have to struggle with the homework. The homework has you doing exactly this. Exactly. I think it's like 2 problems, right? The only difference is that alpha changes. So if alpha changes, then the other percentage changes, then the cutoff changes, right? But I think you guys are okay with this. I think you're okay with it. So I'm going to call it a day now.